Hello, everybody. It's my pleasure to present some recent exciting work on detection and classification of acoustic scenes and events I've been working with. I have quite many things to present to you. I'm happy if anybody has discussions. Meanwhile, I think now in this presenter mode, I cannot see if anybody raises hand, but maybe Shinji, if you want to chair the session, and if anybody
I can coordinate it.
Yeah. Yeah. Actually, yes. Now I can see if there is anybody raises a hand. Yes. Maybe just since I don't know that well, just to warm you up and to get familiar to you. I guess most of you have some background on audio or speech, or can you click yes in this participant? What is this voting option? If you have some background on audio or speech processing, just so that I know it's there in the participant window. I wonder if everybody can access it right now.
No, we can access it, and I would say about half the people in the audience have some exposure, and half don't.
Okay,
good.
Okay, and how many have heard about DCASE challenge? Okay, some of you have, but not many. Okay, so I think then what I prepared should be pretty good. Okay, so basically in this talk I will be presenting lots of different methods how we can analyze information in everyday soundscape. So if there is busy street, or you are in an office or in a cafeteria, there is lots of sounds surrounding you, and they obviously contain lots of information what's happening there. So let's think a bit how we can what kind of information we can analyze from the sound scene. So first of all, you can have methods that try to characterize the entire scene. So if you have an audio signal, if it's from a birthday party, busy street, or home, or then you could focus on individual sources. If there is car passing by, traffic light beep, or dog barking, for example. Or then you could focus on spatial properties of the sounds. So where they are, how far they are, if they are moving or not. And then lots of other stuff, how the sources are interacting together, what kind of attributes they have. So there is actually lots of different things you can try to analyze from soundscapes. And now basically what I'm presenting in this talk is then 4 different methods how we analyze these 4 different aspects. So the first one, entire scene we can analyze by acoustic scene classification, then individual sources by sound event detection, and the spatial properties by localization and tracking of the sound sources. And the last one, all the remaining stuff we try to do with audio captioning. And the first 2 are somewhat established techniques and can be solved with quite established machine learning techniques. So I will be presenting them first quite shortly in somewhat tutorialist manner to those of you that maybe have a bit different background. And then more advanced stuff on localization and tracking and captioning, I will present more advanced methods related to those. Okay, why are we doing this? The reason, at least in addition that it's cool and there is lots of interesting research problems, there is of course lots of applications. So one big area is context-aware devices. So for example, a device can detect the environment it is in and change the processing mode. For example, hearing aids or smartphones do that. So depending if you are at home or in a noisy cafeteria, they will change the processing mode. And similarly then, autonomous cars, robots, they can react to what's happening in the environment. For example, if they hear a hear children laughing from behind a corner, a car can slow down or warn the driver. One other big application area is acoustic monitoring. So there is many commercial technologies, for example, for baby cry monitoring, or if somebody wants to break to your house, then that produces some noise and then it can be detected. Then animal behavior analysis is one big area. So by acoustic or monitoring if there is some accidents, or machine condition monitoring, or what kind of sources produce noise in urban areas. Lots of applications there. And also assistive technologies. So for example, automatic captioning of videos. So Google has had this captioning of non-speech events in YouTube videos already some years. Or then you can do multimedia information retrieval based on the content of sound. Okay, so basically in this talk, like I said, I now reviewed shortly these different tasks, and since not all of you are familiar with this DCASE challenge, I will be mentioning that several times, so I will first introduce that in the beginning shortly, and then discuss these 4 different tasks, especially from the machine learning point of view. Okay, so like Shinji introduced, like this DCASE has become quite successful, and one of the reasons we started doing it several years ago is that, okay, we realized that there is big application potential and lots of research needed in this area. But one of the challenges was really that everybody, because of the large number of applications, all the research groups, they had different data sets and different evaluation metrics and different evaluation protocols, and of course, everybody's favorite methods. So it was really difficult to compare what methods work and what not. And the idea of the DCASE challenge is really then to establish some evaluation protocols, have open data sets and common metrics that everybody could use. So this is an annual data challenge, consists of multiple tasks related to these topics. And we have their open data that researchers can use and have some reference points that everybody can compare how well they are doing. And also one of the ideas is to attract new researchers to the field. And we are putting a special emphasis on reproducibility so that people would share their implementations. So there is the link to the DCASE website. You can find lots of material from there. And for example, we had just last week the DCASE workshop, and the video stream from the workshop is available on YouTube. So you just Google for DCASE 2020 and you'll find lots of interesting stuff from there. And it has been actually very popular. So we have had a really nice increase in the number of participants over the years. So we started small, but it has become actually quite big event. And we are definitely going to organize it next year. So we are currently doing preparations for the next DCASE evaluation. Okay, and this year we had 6 tasks covering these different topics. I'm not going to present all of them, but basically focusing on these 3 where my group has been an organizer. And let's start with the acoustic scene classification, because that's just to basically introduce the basic concepts to everybody. So the idea here is this is basically a rather simple classification problem from machine learning point of view. So you have an audio signal going into a system, and then the scene classification system tries to predict from which acoustic scene this recording is from possible scene categories, which can be, for example, street, home, car, park. This obviously depends, what the scene classes are, depends on the application and the data set. But from the machine learning point of view, this is a single label multi-class, so very standard classification problem. So this is basically easy to approach for those that are just coming to the field, and that's why it has been very popular in the DCASE challenges. And regarding the methods, then it's basic convolutional neural networks that almost everybody is using. So I guess you are somewhat, most of you are familiar with this, but basic idea is that you have audio as the input, then you calculate the time frequency representation spectrogram, and then you have the convolutional layer calculating the activation. You have multiple feature maps, and then you do typically some pooling over time and frequency to reduce the dimensionality and produce a shift invariant representation to learn from high-level representation. And you have multiple of these convolutional kernels. And then in the end, typically fully connected layer, after which you have the number of nodes. Each of them corresponds to one scene class. So basically the output nodes then represent the probabilities of different classes.
So yes. Just a quick question.
Yes.
We are used to doing speech and audio processing. So when we think about the spectrogram, we think typically about frequencies in the 0 to 8 kilohertz range, maybe nothing beyond that, and sampled at 10 millisecond frames. Do you do similar things, or would you do things differently given that this is a different task?
Quite similar. So in comparison to speech, I would say that the time resolution does not need to be as high. So we are using typically something like maybe 20 or 40 millisecond windows. Okay. And frequencies, okay, so it depends a bit on the task. I think with the 8 kilohertz signal, you can do pretty well. 16 kilohertz works a bit better than if you go up more higher, then it's very little gain. So I think it's quite similar to speech. But the main difference is really in the time resolution, because in speech you have quite rapidly changing things, whereas in acoustic scenes, okay, there might be some transient events, but it's more the generic kind of ambience that you are interested in.
Great, thank you very much.
Mm-hmm. You're welcome. And basically also in acoustic scene classification, similar techniques that are used for speech analysis, like when you work with deep neural networks, then for example, data augmentation are very common, and an ensemble of multiple models. So this is what basically most of the people use successfully in the DCASE challenge. And since this is such, I would say, established problem, I will be discussing a bit kind of real life challenges, because we have now in this challenge, we have actually some quite nice case studies related to this. So you probably know that with deep neural networks, you can get very impressive results if your training data is similar to your test data. But then if there is something different in the test data, for example, it's recorded with some different device, there can be pretty huge drop in the performance. And the same is in acoustic scene classification. And what is then specific to acoustic scene classification is these locations from which you record the data. So for example, if I record busy street in Finland, that's going to be very different from busy street in China. So that's why then this is affecting acoustic scene classification on a lot, like where the data is recorded. Related to this mismatch coming from the recording devices, you can deal with that partly with again standard techniques like data augmentation. So you for example simulate different devices by convolving it with some impulse responses and so on, or do some channel normalization. So this kind of basic noise robustness techniques. But then if you really want to handle this kind of for example differences in locations, recording locations, then what we have been using recently is domain adaptation. So you basically, especially adversarial domain adaptation, where you basically try to align the distributions of your training and test data. And you can do that even in unsupervised manner. So we had some nice results related to that at the last WASPA workshop a year ago. And in order to study this kind of, for example, training test mismatches, then we have actually spent quite a lot of time in related to data collection. So obviously now with deep learning, the data is really important, because basically the result, how good your method is very much dependent on how good is your data. And that's why in related to all these tasks, I will be now presenting some data collection efforts that we have been doing. So the first one is this Tau Urban Acoustics Scenes 2020 mobile. So this was used in this year's DCASE. So this is acoustic scene recordings from 10 different contexts: airport, shopping mall, metro station, pedestrian street, public square street, tram, bus, metro, and park. And we recorded data from 12 different European cities to really get diverse data. So we had several recording locations per each city and each scene class. And we recorded 4 devices in parallel. So in this figure here, you see this person wearing the capture devices. So there is GoPro camera on the chest, and then binaural microphones, and 2 smartphones. So one held in hand and one on the chest strap. And we did parallel recordings with these 4 devices so that we can then test the effect of this mismatching devices. And this dataset is available if you go to the DCASE website. There is a link to the dataset. You can try out things yourself. And for example, here in this figure, I'm showing the recording locations in London. So we had research assistants actually going. They spent lots of time traveling around Europe, and it was big effort, for example, to check the recordings that they don't contain any personal information, obviously, because we are recording public places, so we need to be careful. And we are releasing the data. We need to be careful that we are not violating anybody's privacy. Okay, to give you some idea like how these the state-of-the-art methods are working, we also did a listening test comparing machine learning versus human listeners. And it was quite surprising that actually machine learning gave much better results than human accuracy. This is with an older version of the dataset, so the acoustic scenes are slightly different. But it was quite surprising, this result for us. And okay, in this year's DCASE, we had basically 2 subtasks. So the first one, subtask A, focusing on generalization across devices, basically robustness to different recording setup. And subtask B was focusing on low complexity solutions. And that's basically because with powerful models, if you combine big DNN networks, you can get pretty good results. But the difficulty is that these models actually, where they are most used is some embedded devices, for example, hearing aids, which do not really have that much computational power. So then we set up a challenge where we limited the model size to 500 kilobytes to really make people find solutions that work in real systems. And then techniques that were popular is then, for example, some quantization and pruning of the network parameters. They allow reducing the computational complexity.
So, Tuomas, I have a question about the challenge design. How did you kind of confirm that the submission using the model size less than 500 kilobytes? Did you ask the participant to also submit the model, or?
No, we asked them to calculate the number of model parameters themselves. So in that sense, we are trusting the participants.
I see.
Shinjin Nils had a question.
Yes, I had a question. What are the 10 classes in subtask A?
So in the subtask A, they are the classes listed here. So airport, shopping mall, metro station, and so on.
Quick question. For the comparing humans versus the model machine learning data, were the humans given access to some training data just like the machines were?
Yes, they were allowed to listen a couple of samples from each class. So not obviously not the whole training data, because this is some tens of hours of audio. But and okay, maybe related to that, I have also some explanation why the human performance was lower than machines, because I think here, of course, now in this setup, we have a certain definition what is a beach. We have certain definition what is a cafe, and what is a forest path, and I think now in this talks, all the participants had their own idea. I mean, they had some prior understanding what is a cafe and how it differs from some other environments, and then that was causing, for example, some errors. So machine learning can really learn how we define these acoustic scenes, but human participants may have kind of their own prior kind of understanding, which doesn't fully align how we define these scene classes. So in that sense, maybe this comparison was not really fully clear. Or fully fair, but there were some obvious factors affecting this. For example, then this was actually with the data recorded in Finland, and then we had Finns and non-Finns participating, and we measured the difference, and that's definitely affecting the result quite a lot.
Yeah. And also, I can see some of the trends. For example, train and tram, the humans seem to confuse a lot more.
Yes, which is very understandable.
Yeah, forest path and park. So some of them are quite understandable, yeah.
Yes, yes. Whereas then with machine learning, the machine simply learns to recognize that, okay, trams have a specific kind of engine that, but the humans really don't pay any attention to that. But for machines, that might be trivial, really.
Yeah, I also had a similar discussion in the computer vision image classification. Humans, definition of the category is different. Such causes the errors, and that's also the reminds me that
Yeah. Okay. Very good questions. Please ask more if you have any. Okay, but then I would like to move on to sound event detection. Again, go through that. Quite briefly explain the basic machine learning concept. So we are focusing on individual events. So what makes this now different from acoustic scene classification? That individual events are not active all the time. So for example, if you have a car passing by, it's not active throughout the whole recording that you have. And in sound event detection, the goal is now to estimate the start and end times of events like this, and then give a class label to each of them. And okay, to give you an idea what kind of events we could be targeting, I will play here this video where we have manually then annotated some possible sound events.
Morjesta. Joo, mä lähden tulemaan.
Okay, as you saw, even though this was a pretty quiet environment, there was lots of, actually you could perceive quite many events from there. And okay, from machine learning point of view, like how we formulate this problem. So basically, how it is easiest done is that you just predict the activity of predefined sound event classes in some time segments. And in the most generic setting, we can have multiple sound events active at the same time. So basically this means polyphonic detection. And in machine learning terms, this is basically then multi-label classification. So in one segment of audio, we try to predict which sound event classes are active there. And we can indeed have multiple of them active simultaneously, unlike in scene classification, where we assume that there is the whole audio signal is characterized with one acoustic, one class label. Okay, when everybody these days is working with neural networks, then doing this multi-label classification is relatively easy. So in single label classification, you typically have a softmax layer as the last one, and if you want to do multi-label classification, you simply replace that by sigmoid units. So then multiple output units can activate simultaneously. Regarding then machine learning methods, then it's again convolutional layers that are very useful. So typically you have first number of convolutional layers, but what we have found useful is that then it's beneficial to actually add some recurrent layers on top of those. So they enable modeling larger temporal context. And this is important in sound event detection because actually they can be acoustically very similar sound event classes, which you cannot really discriminate properly based on some local information, but you need some contextual information. And recurrent neural networks are good in then modeling this longer temporal context. What is different now here, and okay, this figure on the right basically shows one example topology of some of this kind of convolutional recurrent neural network that we have been successfully using in many different sound event detection tasks. And what is different here from to this scene classification is that we don't do subsampling in time, because we want to estimate the temporal activity of the sound classes. So that's why we don't, we keep the high temporal resolution to allow predicting the, in time frames when the events are active. So these are the main differences to scene classification. So basically multiple events can be overlapping at the same time, and then we produce the temporal activity of the event classes.
Shannon, one question about data. Do you consider output dependency?
You mean how different classes
Yes.
are? Okay, that's a very good question. So basically you mean, I guess this can mean things that when there is, for example, let's say in some urban areas, you hear some siren of an ambulance, then you are likely to also hear some car sounds.
Right.
And in home environment, it's some typical sounds in home you hear.
Or if you hear the phone ringing, you may then hear somebody talking.
Mm-hmm.
Yes. So okay, so I think this phone ringing is good example to sequential modeling. So first one event happens, and then soon after that something else happens. Mm-hmm. And yes, we have been doing this. So this what we have been calling is basically this kind of language model. So in speech recognition, you have language models. So then we have been doing something similar with sound events, and it's possible. My intuition is that this kind of basic recurrent neural networks basically model this kind of sequential stuff, and also kind of joint like events that are happening at the same time. They in principle model that, but it's a bit difficult to really analyze to what degree this kind of basic neural network structures do that. So what we have been doing is then explicit language modeling, for example, where we feed the prediction of the network to the next time step. This kind of explicit modeling, and we were able to improve the results with this kind of approaches. So yes, this kind of things actually matter.
And another question from Nanjin, the ground truth. Did you just using some kind of human annotation as a ground truth, or did you do some the force alignment to finally get the ground truth?
Very good question. So we earlier had research assistants actually annotating some real recording. So of course, like recording audio is very easy, but the annotation is really laborious. And we had earlier research assistants spending lots of time to annotate the temporal activities of different sound classes.
Mm-hmm.
Unfortunately, this is not really scalable. It's so time consuming that you cannot produce large quantities of data this way. So what has become actually more commonly used in the research community is this kind of weak labels, where you don't have the temporal, in the training data, you don't have the temporal information. You just have information whether certain sound class is present in the training data or not. And then you can have a specific machine learning method, basically attention mechanism to predict where the sound is. And you can learn from this weakly labeled data and develop a system that is still able to produce strong labels. So basically these temporal activities. So this is, I would say, then the current state-of-the-art approach.
Okay. And Sandeep, could you also ask question directly? Or Thomas, could you check his the question in the chat window?
Okay. Yes.
Oh, he said that his microphone is not working. Instead, he's asking the question in the chat window.
Okay, so the last question. How do general audios classification models perform on event detection? Is there any evaluation of the self models such as audios at Jamnet for the event detection? Good question. So, okay, so those of you that are not familiar, basically this audios at Jamnet is a model released by Google.
Okay.
So they have released this audio set, which is then 2 million YouTube clips and then annotations of something like 500 sound event classes in those. And Jamnet is then a model trained using this material. And okay, let me check what was again ago. So the question like how well this kind of models can work. So I guess, for example, if we think this Jamnet model, it's trained on material from YouTube. So you can expect it to work quite well on material that is similar to average YouTube videos. I guess this what I can comment. I mean, it's optimized to work on diverse YouTube material. Mm-hmm. Then the question is really then if you are developing, for example, some acoustic monitoring system and you install microphone somewhere, then to what degree then it matches with the YouTube material, it's difficult to say. So anyway, you need to then try it out if you want to use these models in some specific scenario.
Mm-hmm. Okay. And maybe the last question from Paula. Can you directly ask Paula or?
Sure. So it seems that all the frames will have an output label. So what happens if they don't belong to any of the predefined classes? I mean, if you have like a baby crying and it doesn't appear on your predefined model.
So basically, okay, so far I've been talking about supervised classification, which means that you have a specific set of target classes, and then your system is expected to detect only those. If there is something else in the audio, then the model doesn't understand that. And it's basically, okay, it depends on the training material, but for example, in the ideal setting, it's not really activating anything in this case. Of course, like what we have been seeing is that some sound classes, for example, cat meowing and baby crying are close to each other also. Those can cause confusions.
Right. Yeah, I was exactly referring to those ones. Thank you.
Yeah, you're welcome.
Yeah, maybe we can go ahead, and if you guys have some other questions, we can ask later. Yeah.
Good. Okay, so then I would like to move on sound event localization and tracking. So basically how we combine detection with spatial information. So the basic question we are asking, what is the sound and where it is? Obviously, this in order to do this properly requires multiple microphones, but that's actually not that big a bottleneck because many consumer devices, smartphones, smart speakers, actually they have multiple microphones these days. Okay, so this is an interesting area from the point of view that I would say it was among the last ones that switched really to this kind of DNN-based processing. So it was still recently dominated by more conventional approaches. So, for example, where you have a specific direction of arrival estimation methods and tracking algorithm, and then you could do beamforming, which is basically spatial filtering. You filter the sound from the detected location, and then you do classification on top of that. And this kind of approaches actually work pretty nicely. So in this year's DCASE challenge, we had methods doing exactly like this, and they performed quite well. But obviously, like then these days, then more modern approaches are basically deep neural networks that are trained in end-to-end manner and do everything jointly: localization, tracking, and detection. And it's then interesting question like what kind of benefits each of these approaches have. I might be discussing some of these later. Okay, so how you do joint localization and detection with DNNs. So the basic approach is that you have a multi-channel audio going into the system, then the exact features, I will discuss those later, and then you have the network. But then the basic idea is that you have two separate output branches. So the first one for the directional information and the other one for the activity of the sound event classes. So now in this localization branch, basically what is the output is then, for example, XYZ coordinates for each of the sound classes that you are interested, or then direction of arrival angles, azimuth and elevation. These XYZ coordinates, they are better from machine learning point of view because during training, you are minimizing, for example, mean square error. So you're basically calculating distances in the Cartesian coordinate space, and that makes much more sense than, for example, calculating distances between angles. And then this sound event detection output block, that's basically the same and then in this previous sound event detection approach that I was explaining. And now both this information, the directional information and the activity of the events is then over time. And in the most generic setting, you can again have multiple events at the same time, and then the sources can be moving. So when the sources are moving, this would be then called a tracking problem. Okay, so if we go to the low-level features and first processing block is the DNN, so what we have found that works pretty nicely is that you just calculate the short-time Fourier transform and then take separately the magnitude and phase spectrogram and use those as the input feature channels. So if we compare like how this differs from one-channel audio processing, so when you work with one audio channel, you basically have just one spectrogram image, so one matrix of where the dimensions are time and frequency. Now, when we have multiple audio channels, we calculate the spectrogram of each of them. So we have basically multiple input channels. And after that, you can simply use the basic 2D convolutional neural networks as in any kind of with any multi-channel input. And what is good now in CNN is that they actually can learn information across multiple audio channels. So if you think what kind of information is beneficial for localization, it's basically then time differences between the channels. So that's what the human brain, for example, use for localization, or then the level difference. Convolutional kernels can trivially learn this because it's just calculating difference is just basically subtracting two channels from each other. So then, working with this kind of lower level input and having convolutional layers, is pretty good match. And then naturally you can stack multiple convolutional layers on top of each other. So this now figure on the right then shows again one topology of one network that we have used in our practical system. So we have there 3 convolutional layers. So and again, pooling to learn some shift invariant high-level representations. And then after convolutional layers, again, you can have recurrent layers. Now, in this case, there is GRU layers. And what we found that these recurrent layers are useful because they actually can do tracking pretty well. So in conventional tracking systems, they contain information about the position of the source, its velocity and acceleration. And what we found at the recurrent networks actually can learn to represent very similar things. So that's why they are very powerful for tracking. And now these first layers are joined for localization and detection. But then after this initial CNN and GRU layers, we then have separate branches for sound event detection and localization. And they are just using fully connected linear layers. The sound event detection has sigmoid as the output nonlinearity, which is basically truncating the values between 0 and 1, so we can interpret them as probabilities of the classes. Now, in the case of this localization branch, we have for each class, we have 3 parameters representing the x, y, z coordinates. And then the last layer is just linear because we allow any x, y, z values. Of course, if you know the environment where your system is going to be used, then you can, of course, constrain the x, y, z coordinates to certain range. And okay, this is basically in most generic setting, like I said, we can have multiple classes active at the same time. So basically, this is now this direction of arrival branch is doing multi-output regression. So we are predicting the x, y, z coordinates of each class, and multiple of them can be active at the same time. What makes this a bit not really optimal from machine learning point of view, that this regression is using continuous variables, and typical loss that we are using there is, for example, mean square error. Whereas in this detection branch, it's some cross entropy loss. So this balancing these two requires some tuning, and during training they may behave a bit differently. So that's kind of where some manual work might be needed. But basically, this whole system can be trained in end-to-end manner. So it's very flexible in that sense. And okay, it actually works pretty nicely. So for example, here in this figure, I'm showing the predicted activations of the sound events and their predicted angles. So the top row shows the ground truth values, and the lower one shows then the predicted values. So of course there is some noise in the predictions, but in general they align pretty well with the ground truth values. Okay, related to this task, you might be again wondering like how we can get training and test data. And like I said earlier, like doing recordings is easy, but then annotating them is really painful and slow. You could think of synthesizing data, but then there is always questions like how well your synthesized data corresponds to how the methods work in real environments. So there will be then the training test mismatch. And what we actually then, what turned out to be very successful in this DCASE task 3, this kind of hybrid real plus simulation data, where we measured real impulse responses in real rooms in several different directions of arrival. Then we recorded real ambience, again in real rooms, and then we had a data set of real sound events. And we combined all this to generate large number of acoustic mixtures. And let me briefly discuss like how this was done. So for capture, we used this kind of spherical microphone array which has 32 microphones. For the challenge, we used only 4 microphones because that's basically closer to some customer devices that are available. And then we also recorded 360 degrees video, which was basically used to get the reference DOA positions. And then we were measuring the impulse responses by having a generic loudspeaker producing this kind of noise sequence, and we were moving the loudspeaker around the room. And this video is now showing then, for example, one example measurement from a sports hall. Let me play that. So you cannot hear anything, but basically you can see here that the loudspeaker is moving on. Okay, this is the video captured with this video camera that is on top of the microphone. So what you see here on bottom is actually the spherical microphone. It looks very big here because it's so close to the video camera. And then you see there, if you look closely, there is this video-based tracking reference and audio-based tracking reference that we used to get them the ground truth here. And this is in this sports hall, we could really make a full circle around the microphone. So if we go on, you can see that the person is there then disappearing from the left side and appearing on the right side because it's a 360 degrees video. Yes, there he is. And okay, then another example from a lecture room. So there we had furniture, so we couldn't really not make full circles around the room, but for example, move around the room in some straight lines that you can see, for example, here. And okay, and with this video and audio-based tracking, then we get the reference like angles, and for each of the points now in this grid that you see, we basically then have a impulse response measurement that we can use to synthesize lots of different sounds in different positions. And then we just generate events, selecting random sound events in random locations with random speeds, and convolve the impulse responses with convolve the events with the impulse responses corresponding to these locations, and mix with the real ambience. And okay, to wake you up, I will play this sample here. Okay, maybe not so realistic from the point of view what kind of events there are, but actually the acoustic characteristics should be pretty good. And for example, if you listen to a binaural rendering of this kind of a signal, it's very convincing. Okay, related to this area, there is lots of open research questions. So this the research in this field has just started a couple of years ago. Lots of interesting questions like what kind of input features to use. So here in this study, we used the STFT magnitude and phase separately, but there is problems, for example, of the phase unwrapping. So you could think of using, for example, complex STFT, but then you need to figure out how to have neural networks operating with complex valued data because many libraries do not really support this. Or some people represent STFT using their real and imaginary parts. Or then you could use some manually engineered features like level differences and so on. And like one of the questions is really then what kind of network structure to use to model this kind of multi-channel data. Like I said, this kind of standard 2D CNNs are okay, but they are not really scalable. And if you want to make the methods robust to different devices that have, for example, varying number of microphones, then how you deal with that? And one of the limitations of DNN-based method is that the approach that I presented cannot deal with the situation where there is multiple sounds from the same class. For example, 2 dogs barking at the same time. Now this tracking system is only able to predict one location per each sound class. And okay, if you can basically extend it to have a deal with multiple sound sources per sound class, but then you have, for example, permutation ambiguity, like which predicted location corresponds to which class. So if you get ideas how to work on these topics, then there is lots of room to develop these things. Okay, then okay, maybe I need to hurry and switch to the last topic I have, or shall we have some questions at this stage?
Yeah, let's go ahead, and then later we have a couple of the minutes for the questions. So yeah.
Okay, so the last topic is then audio captioning, which is basically then trying to represent all the others' information by producing textual description of an audio signal. So of course, with natural language, you can represent very complex information. And here is just some examples of audio signals and their captions. So if I play this one. And then another one. Just to give you an idea, I mean, you can perceive much more things that is written there, and one could easily extend these captions. There is challenges there because, of course, everybody has slightly different. Each listener has slightly different focus, and these captions are partly subjective. So how we can get a really large number of diverse captions, and there we actually have used crowdsourcing for data collection. So we got the first 5,000 samples from Freesound, which is this kind of platform for sharing sounds. We got diverse set of sounds by controlling this by the tags that people have used there for the sounds. And then we did crowdsourcing using Amazon Mechanical Turk, where we first asked set of people to write captions, listen to audio, write captions, then asking other set of people to fix the captions, and then another set of people then rank the resulting captions to choose the best ones. So first, listen to the audio, write what they hear, then second, some other people fix them, for example, if there is typos, and then in the end, collecting all the captions and other set of people then ranking how accurate the captions are and how fluent is the English in the captions. And this way and just to give you an idea, okay, this is one sample, and these are, for example, 5 resulting captions. So you can see very different descriptions for this single audio. And this is now then the dataset that we used in DCASE task 6, called the Clotho dataset. So 5,000 audio samples and 5 captions per each of them. So in total, 25,000 captions. Okay, regarding methods, then this is definitely the most complex one. So obviously the mapping from the audio to the text is very complex from machine learning point of view. Then also there is very big differences in the lengths. So for example, typical sequence of audio features can be, for example, 1,000 audio frames, but the caption can be, for example, 10 words. So very big difference in this length of the sequences. And okay, regarding the representation of the audio and text, so we are using very standard techniques. So for example, Mel spectrogram of the audio, and then one-hot encoding of the captions, of the words in the captions, and also adding the start of sequence and end of sequence symbols. And okay, so what typically is done, this kind of complex sequence to sequence mapping problems from the machine learning point of view, it's typically this kind of encoder decoder structure. So the encoder is first learning some latent representation from the input sequence, and then decoder is figuring out what it should output based on that. And regarding the methods that are used there, then in the encoder, it's good old CNNs that work pretty nicely. And here it's we have found it useful to use subsampling to basically reduce the dimensionality or reduce the length of the feature sequence so that it's more manageable by the decoder. And then what is really then our state-of-the-art method is then is the transformer-based decoder. So unlike in, for example, in some machine translation, for example, where both the encoder and decoder use transformers. So here, because of these different lengths of the sequences, we found that this approach is pretty good, so that the encoder uses CNNs and then and then the decoder uses a transformer. This works pretty nicely. And this is basically then our latest system which was submitted to ICASP. So this encoder, there is a number of convolutional layers, actually 2 different kinds of CNNs operating in parallel. And then there is the decoder, which is basically following this standard transformer structure, where basically then the predicted word at the certain time step is fed as the input to the system with this positional encoder, and then there is this masked multi-head attention, so that it only looks it only knows what was happening in the past, and then that's combined with the output from the encoder. And okay, how does this work? So this, I have some examples of this kind of system. So this is some captions that are actually surprisingly good. So for example, here I have these 5 ground truths. So these are coming from the crowdsourcing, and this is on the rightmost column is what the system is producing. So let me play this audio sample. So very convincing caption in this case. And for example, now you heard this this sample already. Very good caption also in this case. These are very good examples. And then there is quite many captions where I would say that the prediction is matches with the input, is maybe not so detailed. For example, if I play this first one. And okay, the machine is thinking it's a machine running at a constant speed. Yes, I can't complain about that. Yes. And okay, the second one also then, drawer open and close. Yes, something like that, but maybe not as detailed as what the annotators really said. And then there is some captions which are then somehow weird, not so well matching. For example, if we listen to this one. So some sports events probably, and then now the machine thinks that this is the loud beast snarls as time goes on. Okay, might be, yes. And this one is also a bit weird. Sharpening a knife using a knife. Even though it's actually some bird sounds, probably. Okay, then towards the end of my talk, some future thoughts. So okay, analyzing environmental sounds, it's interesting research field, lots of potential applications. And now this public DCASE evaluation campaigns really allows comparing different methods with public available datasets and metrics. Data is often the bottleneck, how to get annotated realistic data. Then there is some emerging techniques like active learning, zero learning, which are good candidates as alternatives to supervised learning. So I was here focusing only on supervised learning, but of course there is also some other things that can be done. And regarding methods, then in this kind of more classification-related task, then convolutional recurrent neural networks work very, very well in large set of different tasks. But of course, if you have more complex tasks, for example, doing localization, you need to combine different architectures. Or then, for example, in captioning there, where you need then completely alternative techniques. Okay, I would like to thank then researchers in my group and also all the other DCASE organizers who have contributed a lot towards this research. Now, if you are interested in finding out more, there is this recent book that I edited with Mark Plumby and Dan Ellis. And also there in the slides, I had lots of references to publications. You can find them from my webpage. And there is the link to the DCASE community website. And if you are interested in participating in DCASE, here is the tentative schedule of next year's DCASE. Thank you.
Thank you so much. Maybe we can accept the couple of questions. Yeah, it's a little bit past our schedule, but we can accept a few of them.
Okay. Hey, Tuomas, this is Kevin. Thanks for a nice talk.
Thanks.
I have a question about sort of audio-visual stuff. I feel like a lot of these sounds are from physical things, right? Like birds chirping. Is there much work on also looking at the visual domain and combining them? And are there actually applications where this would make sense, or does it really just make sense to say focus on one modality?
Obviously, like of course, there is many applications where basically audio and video, they have complementary information. I mean, there is scenarios where audio is better than video. For example, if there is some obstacles, you can still hear the sound sources. But then, of course, many things that you can't recognize based on sound only. So many monitoring applications, for example, benefit really combining these two modalities. And it's very, very active research field.
Mm-hmm. Okay, thanks.
One last question from the audience. I have like to have a last question. So the localization part, I think it's cool to solve it with a deep learning. But as you mentioned, the conventional method, beamforming and other speech enhancement is also very powerful, right? And actually speech, there are several exceptions, but speech people actually still love to use the beamforming or some other the signal processing statistics in the front end, and then combine it with the speech recognition. Even they kind of move to the deep neural network. The beamforming and the deep neural network somehow combined now in the like our approaches or Amazon's approaches are like try to solve it with keeping the beamforming, the mathematical equations and so on. Do you have some first how about the general trend of the participants are still participants are focusing on the end-to-end training, or some people working on the conventional approaches? And what do you think about your personal opinion or the concept of how we combine these kind of approaches?
Good question. So this task on localization detection has been organized only twice, so it's a bit difficult to predict what are the general trends. A majority of the people are using DNN-based techniques, but that might be because basically we provided this baseline which was based on DNN, so perhaps many people then just took that and as the starting point of their own method. So of course developing a system from scratch requires quite some expertise. But then I think there is room for knowledge from both this kind of conventional approaches and DNN-based approach. Maybe I think one of the reasons how I think this kind of a more traditional beamform is still used, it's maybe a bit different set of people who have good knowledge of beamforming techniques, and then other group of people who are then doing this more pattern recognition with DNNs. Okay, now these days maybe this knowledge is spreading more so it's people are making really joint systems, but it might be simply then that it's different communities developing these two techniques. Of course, this kind of traditional beamforming techniques that have some benefits that they allow separating signals, for example, without introducing that many distortions when you do spatial filtering, if you want to do robust processing. And I think it's still, for machine learning techniques, it's very challenging scenario. If you have two sources close to each other, then how machine learning can figure out that they are really two different sources. But then this kind of array signal processing people, they have more kind of advanced methods to really deal with this kind of specific scenarios. These are, I think, some points that I can think of related to this topic, but it's difficult to see like what is the future.
Okay, cool. Okay, that's it. Thank you, Tuomas, again, and Tuomas.
Thanks a lot for inviting me and giving this opportunity.
Yeah, our pleasure. And we can move to the other room to continue the discussion with several individual meetings.
Sure.
Thank you so much. See
Thank you.
Everyone.
Thank you.
Bye.